Welcome back to Computer Graphics and Visualization subject. In last video we have discussed Module 4. In that Module 4 we have discussed 3D viewing. Again in that 3D viewing we have discussed parallel projection. Today we are going to discuss from the same module. Today we are going to discuss perspective projection. Right? What do you mean by? In last video we have discussed briefly about perspective projection. What is a perspective projection, what is a parallel projection, all those things. Now today we'll start discussing in detail, that is the perspective projections. Right? Although a parallel projection view of a scene is easy to generate and preserve relative proportions of objects, it does not provide a realistic representation. In last video we have with one example I have told that in parallel projection you can maintain the relative proportions of objects. Means if one line ends in real world, or one is at 10,10 and one line other end is of that line is at 20,20, same distance you can maintain in your projection plane. That means the length of that line can be retained as it is on parallel projection when you are going to display, but it doesn't provide a realistic representation. That doesn't looks real object, because our eye looks in a different way. That is the reason we are going for perspective projection. Right? To simulate a camera picture, we need to consider that reflected light rays from the object in a scene following flow converging path to the camera film plane. Mean in real life, whenever you are taking a picture of any object, then that picture of that object is printed on the film, which is normally present at the back side of your camera. Right? Then how that is presented, whatever rays you have captured from that rays are coming, then those rays are converged at some point on your film. Means those rays are coincided at a particular point in your film, right? Any camera. That is what real camera does. Right? We can approximate this. Means if you have taken 4 lines, for example, if you are taking a rectangle, then all 4 lines will come and join at only one point. That is called convergence. Right? On a film normally it will happen, in real life camera. Right? We can approximate this geometric optics effect by projecting. Then that can be implemented in OpenGL. How that our real life camera does, same can be implemented in OpenGL or any software. We can approximate this geometric optics effect by projecting objects to the view plane along converging paths to a position called the projection reference point or a center of projection. Right? We can approximate, means whatever I have told, means the rays will come and join somewhere. All rays will come. For example, if you are taking a picture of a particular tree, then from all the sides of the tree, rays will come and they will converge somewhere in your camera film. That is what the convergence point. Right? That can be approximated in any computer graphics applications. Right? By projecting objects to the view plane. There is a view plane. Means, for example, if you want to take here image, then by projecting objects to the view plane along converging path to position called the projection reference point or the center of projection. In next slide image may be there, you can see here. For example, first image, there are 2 lines. You want to take those 2 lines image on your view plane. Means you want the image of those on view plane. Right? Then in that case what you have done, I have taken a rays from that line on my view plane. Then normally those rays will be converged at some point. That is called projection reference point. Such 2 line object images we have taken on our view plane, whatever rays we have passed along with that line, they will converge somewhere. That is the projection reference point. Then the size of line is not same as that of your origin. The size of line may not be same as that of the original, whatever real line is there. Right? Because you have taken that line image somewhere in between that original line and the projection reference point. Right? Depending on that, this size will increase or decrease here. Right? Then one more image I have taken. For example, if you are taking a house image in perspective projection, center of projection is a viewer. Normally all rays will come and join at our eye, right? That is a projection, center of projection. Then whatever rays are coming from that object, those are called projectors. Then view plane, somewhere in between our object and our eye will be there, you project, right? That is means again this is what the projection plane. Then projection reference point, right? And then object is somewhere, view plane is somewhere, then project reference point is somewhere. That projection reference point is means all lines, all rays, projectors join, converge some point, normally converge some point, that is called projection reference point. That again I have given same one example in last class and in lab also. If you stand at one point on a railway track which is straight line, which is exactly straight, if you stand at one place at a railway track, but you see for a longer distance, you see for a longer distance, after some distance the tracks you will feel that tracks are merging, joining, that is called projection reference point. Means that point is called projection reference point or the convergence point. There you will feel that the lines, even though they are parallel in reality, but you will feel that they are joining somewhere. That is called projection reference point. That is the center of projection. That is called center of projection, right? Then objects are then displayed with the foreshortening effect. That's why I told the objects are then displayed with the foreshortening effect, because depending on where that projection plane is there, projection plane lies in between your object and projection reference point. Projection plane will lie between projection reference point and object, in between that is there. That's why this size of object is foreshortening effects, right? And projections of a distant object, or that's why projections of a distant object are the smaller than the projections of the objects and the near size. That's why the projectors, the projection, if you project a longer distance object, then they will look smaller. If you project a very near, if your object is very near to your eye, then it will look bigger. If object is very far away from your eye, then it will look very smaller. That is the meaning of this line. Means, right. Then next is perspective projection, transformation coordinates. Next is perspective projection, transformation coordinates. Means we have to transfer perspective projection to perspective transformation coordinates, right? That is what normally view coordinates, in the view coordinates, those formats points are in the view coordinates. Then we have to convert it to projection transformation coordinates, right? Means now till that point the points are in 3D. After that projection, after this projection we are converting into 2D. That we have to do, right? We can sometimes select the projection reference point as another viewing parameter in a graphics. We can sometimes select the projection reference point as another viewing parameter in the graphics. Means projection reference point means converging point can be treated as another viewing parameter in a graphics package, but some systems place this convergence point in a fixed position, such as the viewpoint. Means by default, if in some packages you can adjust this one, or by in some system by default the viewing reference point is by default projection reference point, right? Such as the viewpoint, means from where you are viewing, that automatically will become the projection reference point. In some of the systems you can adjust, right? That's why the projection path of a special position x, y, z. For example, if you want to take the projection of point P in this image, that is x, y, z on projection plane, right? To generate projection reference point at x projection reference point, y projection reference point, z reference point here at the right side, my right side, right? That is x PRP, y PRP, z PRP. That is reference point. There the actual reference point means there they are going to converge. If there are 2 points, all points will go and converge at that point. Since we have taken only 1 point, that's why we have drawn only one line. If there are many points will be there, all will converge. Means that is nothing but your eye. Means all rays will come and converge at our eye. All rays, how many objects you are seeing, all object rays, projectors will come and converge at our eye. That is what the projection reference point here, right? That we have taken there. Then that is means from that point we are nothing but we are viewing from that point. That reference point is nothing but we are viewing from that point. That's why x view, z view, y view. Which point we are viewing? We are viewing point P. Then we are taking an image on that point at project view plane. That is view plane. That is colored we are shown here. That is xp, yp, zvp. Means I want that P to be projected in this plane at a point xp, yp, zvp, right? Then these xp, yp, zvp are not exactly same. They may not be exactly same as that of x, y, z. But this was the case in parallel plane. Parallel plane, if object is somewhere in real life, that object is somewhere here, then the projection also same. Means if object is at x, y, z, then after taking projection, the object remains at x, y. Since x, y means in projection plane is a 2D plane, that's why in real life, if that object is at some distance in x, in some distance in y, again at the, it may be same at projection plane also, because you are taking a parallel projection. But in this case it is not parallel, it is going some inclination. That's why those x, y, z may not be same as xp, yp, zvp may not be same as that of x, y, z. Those we have to calculate here. Then what is xp, what is yp, what is zvp? When you have projected for particular line, then what is those points on my projection plane actually, right? I know x, y, z, where is that x, y, z, but we don't know what is xp, what is yp, what is zvp. That depends on where your projection reference point you have taken, where your object is there. Depending on that, that value of xp, yp, zp will vary. For example, your projection plane is towards a reference point. You can move that projection plane anywhere between your object to anywhere between your projection reference point, right? If your projection plane is towards x reference point, then those values of xp, yp, zvp are different. If your projection plane is towards p, then values may be different, or in between these, that xp, yp, zvp may change. That's why we have to calculate what is that value with respect to reference point, with respect to object, then where you have taken exactly that projection plane. Depending on these three parameters, the xp, yp, zvp may change, right? Because x reference point may be somewhere, p may be somewhere. In that p and x reference point, you may vary your projection plane. That's why xp, yp, zvp are not always same. That varies depending on the relative positions of these 3 points, right? That's why we have to calculate what is that, right? The projection lines intersect the view plane at the coordinate position xp, yp, zvp. As you know, the projector line has intersected the projection plane at the point xp, yp, zvp, right? Where zvp is some selected position for the view plane on the z view axis, means where you want that projection plane from z. Do you want that projection plane at origin? Do you want that projection plane from origin to towards z, positive z, or do you want that projection plane towards negative z, right? That means that projection plane can be varied. This is additional flexibility is available in OpenGL. As I told, other than camera, in camera you may not adjust this one, but in OpenGL you can adjust projection plane where you want to take that image. That can be done in z axis, along the z axis, because always we are looking in negative z direction. As I told, always we are looking object in negative z direction. That's why that projection plane can be adjusted in between the viewer and the object, right? That is what the meaning of that line, right? We can write equations describing coordinate positions along this perspective projection line in a parametric form, as means then on this where is exactly new points on projection plane, where those points, instead of taking xp, yp, zvp, here we have taken x dash, y dash, z dash. Generally instead of taking that xp, yp, zvp, we have taken x dash, y dash, z, means x dash, y dash, z dash are the points on projection plane. Then where exactly they will come, right? That we have to calculate always, because that x dash, y dash, z dash depends on where your projection plane is there, where the reference point, where the object. Because if you are changing the projection plane in between this, then x dash, y dash, z dash may change, but those are not parallel, they are inclining. Because if you are going towards the reference point, the object is very small. If you are coming towards the object, the image will be very bigger. That's why x dash, y dash, z dash is not always same in the projection plane, right? That's why those we have to calculate. How to calculate? X dash is nothing but x minus bracket x minus x projection reference point into u, right? Then y dash equal to y minus y projection reference point into u, z dash equal to z projection plane into u, where u is 0 to 1, means u can vary from 0 to 1. Then what is 0? Coordinate position x, y, z represents any point position along the projection line. Coordinate points x dash, y dash, z dash, actually that is not x, y, z. Coordinate points x dash, y dash, z dash represent any point along the projection line right? Then when u is 0, for example, when u is 0, we are at a point p equal to x, y, z. Means when u is 0, you are taking projection plane is towards actual original point. When u is 0 means you are taking the projection of that object towards the original point at the other end of the line. At the other end of the line. When u is 1, and we have the projection reference point coordinate xp, rp, yp, zp. Means when u is 0, we are taking the projection towards the object. When u is 1, we are taking the projection at the reference point, right? This is the meaning. Means in this, when u is 0, you are taking projection at p. You are taking means you are taking near to that p. When u is 1, you are taking that projection towards reference point, that side. You are taking it towards that side, right? That is from a reference point. This is the meaning, right? That is at the reference point. But when u is 0, you are taking towards the that point. This is the meaning of this. And we have the projection reference point coordinate xprp, yprp, and zprp. On the view plane, normally on the view plane, z dash equal to zvp. On the view plane, z dash equal to zvp, and we can solve the z dash equation for parameter u at this position along the projection line. Means then, as I told that u will vary from 0 to 1. As I told that u will vary from 0 to 1. Then what is u? Then where exactly you have taken that point, right? In this, from object to reference point, in this area, object is here, your reference point here. Then you can take that projection in between these 2 points just by changing the u. If u is 0, you are taking this side. If u is 0, you are taking that projection toward this. Means you are near to object. You are near to object. If u is 1, you are near to reference point. You are near to reference point. Then by varying this u, you can place that projection plane anywhere between this object and reference point, right? Then what is u? How to calculate that u, right? That u can be calculated as z dash equal to zvp. Means you know the z. Means on a z line where that plane can be placed, because you are moving in negative z direction. Then do you want that that plane exactly z equal to 0, or z equal to something towards this side, or z equal to something towards that side? Z value can be known. That's why z dash equal to zvp, right? By substituting this value in the third equation in previous this, by substituting that z dash value in this line, you can calculate very easily u from this equation. That is z dash equal to z minus zvp. Once you know the z dash, then you calculate for u. That we have done here. That is u equal to zvp minus z divided by zprp minus z, right? Zprp minus z. By substituting z dash in that third equation in previous slide, you can calculate u. Then you know the u. Means where exactly you have placed that projection plane. Whether that projection plane is towards p, whether that projection plane is towards that projection reference point, or projection plane is somewhere in between this. That may be 0.5, that may be 0.25, whatever. In point range, where is it? Where is that one? That is a u, right? Substituting this value of u onto the equations for x dash and y dash. So if substitute this u into the equation x dash y dash, we obtain the general perspective transformation equations as, for example, if I substitute that u value in x dash and y dash, then those xp and yp, whatever xp and yp, generally xp and yp we can calculate that xp equal to x into zprp minus zvp divided by xprp minus z plus xprp into zvp minus z divided by x zprp minus z, that is xp. Means xp value on that projection plane. Then yp equal to y into zprp minus zvp by zprp minus z plus yprp into zvp minus z by zprp minus z. This is the general point. Means those are the points on the projection plane, right? Then perspective projection equation, special cases. Perspective projection equations, special cases. Here we can consider special case of perspective projection equations. What are those special cases, right? Various restrictions are often placed on the parameters for perspective. As I told, there are various restrictions are often placed on the parameters of perspective. As I told, means you can vary that projection plane in between your object and p reference point. That can be varied, right? Depending on this, we have the special cases, right? depending on the particular graphics package, positions for either the projection reference point or the view plane may be completely optional, right? Positions for projection reference point are optional here, completely optional, right? To simplify the perspective calculations of the projection reference point, for the projection reference point could be limited in the position along the z view axis, right? Means only to simplify that projection reference point, only you limit that projection reference point must be in the z view direction. It should not be in the x and y. Only restrict so that you can very easily calculate xp yp anytime, right? Then for example, xprp yprp equal to 0. xprp yprp equal to 0 means if your projection plane is always on xy plane, if your projection plane is only on xy plane, then reference point of xy is always 0, right? Because you are seeing in negative z direction, then your projection plane is somewhere here. At that time x reference point and y reference point are 0. X reference point and y reference point are 0 always on xy plane, right? On xy plane x and y are 0. If these are 0, then xp equal to x into zprp minus zvp by xprp minus z. Then yp equal to y into zprp minus zvp divided by zprp minus z. Means nothing but when you are at exactly origin, nothing but if your reference point if your reference point converging point is exactly at origin, then this will happen, right? Or if your view plane exactly at origin, right, this will happen, that xp equal to this whatever we calculate this, right? Then sometimes the projection reference point is fixed at the coordinate, and that is what if your xp yp is 0. Then next is sometimes the projection reference point is fixed at coordinate origin. Means projection reference point is fixed at coordinate origin, that is not at origin, that is at x and y plane, that is exactly at x and y plane. Z may be somewhere in that range, that first one. But second one, if your reference point projection reference point at origin, at that time all three are 0. This is at origin, second one is at origin, first one is not origin, it is at xprp yprp 0, but z may be anywhere, that is the first case. Then second case, if your projection reference point is at exactly at origin, all 3 points are 0 0, means xprp yprp zprp are 0 0. Then at that time xp equal to x by x into zvp by z, yp equal to y into yvp by z. That is what new x and xp and yp in second case. In third case, if the view plane is the uv plane and there are no restrictions on the placement of the projection reference point, then we have, means if the view plane is the uv plane and there is no restriction on the placement of the projector reference point, then we have that is zvp equal to 0. zvp equal to 0 means anywhere in between, view plane is anywhere in between this uv plane. Then if zvp is 0, then xp equal to x into zprp by zprp minus z minus xprp into z by zprp minus z. This is what new point when zvp is 0. Right? This is xp and yp. Then one more case, with the uv plane as the uv plane, and the projection reference point on the z view axis, the perspective equations are, with the uv plane as the view plane and the projection reference point on the z view axis, the perspective equations are nothing but xprp yprp and zvp equal to 0. xprp and yprp and zvp equal to 0 means it is at xp yp equal to 0, then zv up, that projection is at origin, projection is exactly or taking at origin, then xp equal to x prp divided by that. This is the equation. Means projection reference point may be somewhere, but you are taking that reference at origin, right? This is what the meaning of this. then of course we cannot have the projection reference point on the view plane. We cannot have the projection reference point on the, means you cannot take the projection reference point itself on the view plane, right? Projection reference point may be somewhere here, then projection you can take at projection plane, right? You both cannot be at same point, right? In that case the entire scene would project to the single point. In that case entire scene will project to the single point, right? The view plane is usually placed between the, as I told, the view plane is usually placed between the projection reference point and the scene, right? View plane normally placed in between the real life object and the projection reference point. In between this view plane maybe you can place anywhere, right? But in general the view plane could be placed anywhere except the projection point. Except the projection means if in real, as I told, in real this is the flexibility available in OpenGL. View plane may not come behind the projection reference point. You can take projection reference point is somewhere here, you can take view plane this also, means object is here, your projection reference point is here, you can take view plane behind this one also, that is also possible. But when you are taking behind the projection reference point, if you take view plane backside the projection reference point, then your object will be tilted, your object will be exactly reverse. Means if your object is like this in front of this, then projection reference point are here, you are taking projection here. At that time if your object is like this, then you will get object like this. Normally in our eye same thing will happen, means the projection reference point is in your eye, then the film means image will be produced at backside of that projection reference point. If I am standing like this, my projection will be exactly reverse in our eye. This is what happens, that is the meaning of this line, right? Then perspective effects also depend on the distance between the projection reference point and the view plane as illustrated, right? As I told, if your object is very near to your projection reference point, then object will be very bigger, right? If your object very bigger, if your object goes away from your thing, then the object looks very smaller. If your projection reference point is very far away from the film, then you will get a parallel, projection. This is what the meaning of this, right? Then vanishing point for perspective projection. What do you mean by vanishing point for perspective projection? We will discuss, right? When a scene is projected onto a view plane, using the perspective mapping, lines that are parallel to view plane are projected as parallel lines, right? When a scene is projected onto a view plane using perspective mapping, lines that are parallel to view plane are projected as parallel lines, right? But any parallel lines in this scene that are not parallel, any parallel lines that are in the scene that are not parallel to the view plane are projected onto converging lines, If they are not parallel, then definitely after some time they will go and join somewhere, right? That converge lines, right? Then the point at which a set of projected parallel lines appear to converge is called vanishing point, right? The point at which a set of projected parallel lines appear to converge is called a vanishing point. Each set of projected parallel lines has a separate vanishing points, right? In next slide we will see, right? For example here, right? That is one object, that is a cube. I want to project. If I take that image, actually the edges of that cube are parallel. But if I extend those, after projection, after taking the projection on projection plane, if I extend those parallel lines, definitely after some time they will join, they will merge, they will converge. That is called vanishing point. In reality the lines edges are parallel, but after taking the projection, if I extend those lines, then those are called vanishing point, right? That is a single 1 point perspective projection, that is a 1 point perspective projection. Like that 2 point perspective projection, 3 point perspective projections are there. Next we will see the 2 point perspective projection. Simply if I tilt that cube, means I want to see the more number of faces, of that cube. In that case, actually means I want to see both the side, means I want to see this side, I want to see this side, means I want to project two sides of that cube on my projection plane. At that time again the edges of those cube are parallel, but if I extend those edges, then again they will merge, right? if I extend x face, means which is face is at x side, which face is at x side, if I extend, they will merge at z direction. They will merge somewhere after some distance in a z, that is called z vanishing point, right? I extended actually this is x direction, this is z, this is z, this is y, right? Actually I am extending x face, but if I extend this one, they will merge at z, they will merge at that is what, z axis vanishing point. Again at the same time, if I extend front face, if I extend front face joins, then this will extend at join at y x axis, this will join at x axis, that's why x vanishing point, that is x, means this is 2-point perspective projection. There are 2 vanishing points in this case, right? Like similarly you can form 3 vanishing points, means if you see from top, then one more vanishing point you will get at y direction, one more vanishing point you will get at y, like that we have different vanishing points, means single point perspective projection, 2-point perspective projection, and 3-point perspective projection, right? This is vanishing points. Then perspective projection view value, perspective projection view value, like that how we are calculated for parallel projection view value. Similarly here also we have perspective projection view value, right? This is bounding planes for the view value are not parallel because the projection lines are not parallel here. Here in parallel projection we have parallelepiped means that is a rectangular box we have, that is a view value in this case, but it is not parallel. All planes are not parallel here. The bottom, top and sides of the view value are planes through the window edges that all intersect at the projection reference point, right? The top view, top plane, side plane, that side plane, bottom plane, all planes will converge at the center of projection. All planes will converge at the center. That is the meaning of that. Means the bottom, top and sides of the view value are planes, even though they are planes through the window edges that all intersect at the projection reference point. Even though those are planes, this is the top plane, side plane, bottom plane, but they will come and converge at one point. That is what center of projection. This for the view value, that is an infinite rectangular pyramid with its apex at the center of the projection. With figure you can see this is view value, means these are the projected rays. This is a one plane, top plane, then this is side plane, then that is again one more side plane, this is bottom plane, then all planes will merge here at the center of projection. All planes will merge here. This is called view value. This is like a pyramid. This is not a parallelepiped, right? This is like a pyramid, right? Then here by adding near and far clipping, like in parallelepiped, in parallel projection we have added far end and near end. In between whatever object comes, that we have taken. Similarly if you do here also, by adding near and far clipping planes that are perpendicular to z view, because you are looking in negative z direction, near end, far end, that is exactly perpendicular to the z view axis and parallel to the view plane, we chop up parts of the infinite perspective projection view value to form a truncated pyramid. That is our first term or view value. This is called a first term or the view value. Means if you add near clipping plane and far clipping plane, then whatever clipping window, this is what projection, the entire thing is a clipping window, means whatever outside comes from outside, whatever outside objects are there, those will not be taken. That is a clipping, means we are doing a clipping here. How we are done in 2 dimensions, how we are doing in parallel projection, like that here also we are doing clipping, means whatever out of the top edge, plane, whatever below the bottom plane, whatever left side, whatever outside the right side, whatever after far, after before near, whatever objects are there, those will be clipped. Whatever object is there in this first term, rectangular first term view value, whatever object is there in this value, only that will be projected here. That will be projected. That is what clipping window, right? This is called a first term. This is called a first term or clipping window, right? Projection reference point is here, right? In between this you can take any image, right? This is value, right? Then perspective projection transformation matrix, right? Perspective projection transformation matrix. Unlike a parallel projection, we cannot directly use the coefficients of the x and y coordinates here. You cannot use directly x and y coefficients how we use it in parallel projection, because denominator of these are functions of z, because denominators of these are functions of z, but we can use the 3-dimensional homogeneous coordinate representation to express the perspective projection equation in the form. Homogeneous coordinate system can be used to represent the perspective equations in the form xp equal to xh by h. H is a homogeneous coordinate, xp is xh by h, right? Then yp is yh by h. This is a homogeneous coordinate representation. We are done in 2 dimension also, we are doing same in 3 dimension also, where the homogeneous parameter has the value, that is h. H is nothing but zprp minus z. That h is nothing but zprp minus z. The numerators in equation 22, if you see the textbook, that is 7.22. 7.22, the numerators in equation 22 are the same as the equations in 17. These are with respect to textbook I have written. Here also same equations I have taken, but I am not mentioned the equation numbers. That's why I am mentioning here the numerators in equation 22 are the same as in the equation 17, right? Then by taking those equations, then xh is x into prp minus zvp plus x prp into zvp minus z. Then yh is y into zprp minus zvp plus yprp into zvp minus zp. That if you want, you can see these equations. We are talking about these equations, right? These equations, right? Then here, thus we can set up a transformation matrix to convert a special position to homogeneous coordinates, so that the matrix contains only the perspective parameters and not the coordinate values. Only the perspective parameters and not the coordinate values. We don't want coordinate values because those are the perspective in projection, right? The perspective projection transformation of the viewing coordinate position is then accomplished in 2 steps. The perspective projection transformation of a viewing coordinate position is then accomplished in 2 steps. In first step, we calculate the homogeneous coordinate using perspective transformation matrix. First, we calculate the homogeneous coordinate using the perspective transformation matrix like this. For pH, homogeneous coordinate for perspective transformation is pH equal to m perspective into p, right? M perspective into p, where pH is the column matrix, representation of the homogeneous point xh, yh, zh, h, and p is the column matrix representation of the coordinate position, that x, y, z, 1. That is homogeneous representation of 3D point. Any 3D point in homogeneous coordinate we will represent with the 4 values, that is x, y, z, and 1 is homogeneous coordinate. Then homogeneous coordinate for pH is xh, yh, zh, h, right? Then after that, then second step, after other processes have been applied, such as the normalization, transformation, and the clipping routines, after normalization, then after clipping, the homogeneous coordinates are divided by a parameter h. Homogeneous coordinates are divided by a parameter h to get the actual values of x, y, z, right? To obtain the true transformation coordinate positions. The following matrix gives one possible way to formulate perspective projection. There is one possible way to get the perspective projection matrix, right? What is that? Here, m perspective equal to zprp minus zvp 0, that is a x row, then y row, then x y row, then z row, then homogeneous row, that is what, minus 1 zprp. Here what is then sz, tz. Parameters sz and tz are the scaling and translation factors. Parameters sz and tz are the scaling and translation factors for normalizing the projected values of z coordinates. Means in some time you have to scale your, means you have to zoom in normally, we have to reduce the size. In some means, then in some time we may translate. That means you projection plane, if you are translating, this is what the meaning of this. Then specific values of sz and tz depends on the normalization range we select, right? Specific values for sz and tz depend on the normalization range we select. Above matrix converts the description of the scene. Into the homogeneous parallel projection coordinates. The above matrix converts the description of the scene into homogeneous parallel projection coordinates, right? This is what perspective projection. Then since still it is, means still to convert normalization, still we have not done normalization of this perspective projection. That can be done in future topics, right? But today we will stop here. In next class we will discuss how to normalize. Again there are oblique perspective projections are there. Then after discussing them, then how to convert, how to go to normalization, how we are done in parallel projection, that can be done in perspective projection. Means now we have formed the first term. With respect to first term, I have that object. With respect to first term, that object we have covered in this first term. but then that has to be converted to normalization form, right? That normalization first term, that may be in the range between -1 -1 -1 to +1 +1 +1, that is a normalization cube or normalization first term. Then these objects has to map later, how we are done in parallel projection. Same thing can be done in perspective projection. That topic we will discuss in next video, right? By this we will end today's session. Thank you.